So far we've looked at synthesis, decomposition, combustion, reactions of acids, now onto displacement. So displacement occurs when an element or an ion displaces another from a compound. There's two types of displacement. One is called double, one is called single. Single displacement is when we take a metal and put that metal into a solution, and what may occur is the metal ion from the solution will come out and the solid metal that you goes into solution. So here's the example, is that iron, if I put an iron nail into a copper sulfate solution, copper comes out of the solution and iron goes into the solution. Yeah, it displaces the copper ions to make copper solid instead. So there's that example. So I've got an iron nail in a copper sulfate solution.
What's the first one?
Single or double? We haven't talked about double yet. So if I put iron into a copper sulfate solution, iron is more reactive, right? Iron is more reactive. So the more reactive metal as a solid will displace the less reactive metal if it's in solution. So if I did it the other way around, if I put a piece of copper into an iron sulfate solution, nothing would happen. Yeah? So it must be more reactive. Georgia, thank you. Observationally, what we notice is you can see how, in this diagram, how the blue fades away. Yeah? Becomes more of a yellowy coloured solution. I know it's hard with the background and that's a condensed video or whatever. But you should notice that it becomes more pale. And that's because the copper ions are blue, and as they deposit onto the metal nail, we're getting less blue in our solution.
Oh, sorry. That's just copper.
This is iron nails in a copper sulfate solution. So what you see, these crystals of copper are forming on the surface of the nail, and the nail is oxidizing and going into the solution. We can predict them by looking at what's called the activity series. Not something I'm expecting you to know, so we're going to sort of skip through this fairly quickly. But we know a bit about reactive metals. We know that group 1 and group 2 metals are highly reactive. So you should know that much. Thanks. Iron ores. So we've got one of the biggest iron mines in the world, in Australia, particularly in WA. Yeah? It's the reason why Uluru is red. It's actually sandstone. So if you scratch below the surface of Uluru, it's yellow. It's sand. Yeah? The reason it's red is from all of the iron ore dust, that's this reddish, dusty compound.
So wait, with Uluru, like the rock Uluru, would that be like, why couldn't we do it?
I mean, you can, but it's just sandstone. There's nothing valuable about it.
It's like yellow inside.
Yeah, it's yellow. It's a sandy colour.
Because it has a...
Yeah? It's just got this iron ore from all the westerly winds that have blown onto it over millennia, right, that have deposited onto the rock. Sorry? I don't actually remember. I have visited there a few years ago.
Wait, is it so red because it hasn't oxidized?
It hasn't oxidized. It's got a iron ore coating over thousands of years.
Rust is like a reddish color.
Yeah.
Because it's been oxidized.
Yeah, that's different. Rust is iron hydroxide. Yeah, that's really flaky.
Yeah.
Iron ore is a mixture of different compounds. That's iron oxide, iron carbonate, iron sulfate, and etc. So huge mines, because iron is the core component for steel. Yeah, steel is made up of iron and carbon. So iron is a massive industry. Mining in general, massive, massive industry. In Australia, we are one of the biggest exporters of primary metals and stuff in the world. There we go. We should notice that copper, mercury, silver, gold, we can mine these metals in their pure form in nature. because they're unreactive. Yeah? So gold and silver rings, you notice, don't tarnish readily. They don't oxidize readily. And they can be easily polished. Things like magnesium, aluminium, although we have aluminium foil and aluminium windows, aluminium's quite reactive. How it stabilizes is it oxidizes readily, and it's that aluminium oxide layer that protects the underlying aluminium from further oxidation. Iron, when it rusts, is slightly different because the properties of iron hydroxide, that's rust, right, is actually very brittle. So as rust forms, it brittles, flakes off, and the underlying iron continues to corrode. Put it away. Unreactive elements have only been known for maybe up to 200 years at most. Yeah? Sorry, other way around. Reactive metals, only a couple of hundred years. Development and technology, and particularly electricity, has enabled us to isolate reactive elements. Unreactive elements have been known for thousands of years. Right, because they exist as they appear in nature, gold, silver, etc. Double displacement. So it's when I've got two solutions, as I mix them, they swap. One product often will precipitate out. And so this was our prac we did last week on precipitation. Something will only precipitate out if that particular combination of ions is insoluble. So here's an example. Sodium chloride and silver nitrate, that was in the amber bottle that we looked at last week. Sodium chloride, or you might have mixed it with hydrochloric acid, you would have got this white precipitate. And that's silver chloride, because silver chloride is insoluble in water. So that's why it comes out as a solid. So precipitation is a form of double displacement. Double displacements may occur without a reaction actually occurring if both of the possible products are soluble as well. There's another example, sodium hydroxide and cobalt chloride. Cobalt hydroxide comes out as a solid, as a blue, grey solid, and sodium chloride remains in the solution. We can predict precipitation reactions. I said last week that I wanted you to just avoid, not worry about doing the prediction side of things. When it comes to the exam, you will have questions on solubility. There's a quiz there and various other revision resources. We'll talk about that more as time goes on. So solubility rules. What I want you to do is write these down. Yeah? You will be provided a solubility table on your exam to assist you, but there's a couple of good mnemonic devices to help you remember. One is called SNAPE. SNAPE, shush, and chops are our three mnemonic devices, really useful for remembering solubility rules. SNAPE is always soluble. So there's our table. You get something similar to that for your exam. SNAPE is always soluble. SNAPE stands for sodium ions. So this is always soluble. Sodium. And it's the sodium ion, not the sodium metal. Nitrate. That's NO3 minus. Ammonium. That's NH4 plus. Potassium. So we see we've got this trend with most of our group 1 metals will be soluble, right? And this last term, ethanoate, also called acetate. And that's CH3COO minus. Always soluble. Always. Right? So any salt, any ionic compound that's got one of these ions as a part of the compound will always be soluble. Okay?
Oh wait, you have to.
Yep, I have written it on the board as well.
Oh, okay.
SH. Right? My way of thinking is it's mostly soluble. Sulfate. Mostly soluble is sulfate. SO4 2 minus. And H4 halides, which is a general term for things like fluoride, chloride, bromide, iodide. There's some exceptions to the rule. And the exceptions to these are generally heavy metals. So things like lead, mercury, barium. So if I combine these with lead, mercury, barium, or silver, we'll get a precipitate. So these are heavy metals. Other things will generally be soluble. And lastly, chops are mostly insoluble. And that stands mostly insoluble. Carbonate, hydroxide, oxide, phosphate, and sulfide. Notice in all three examples I've got an S, but the S stands for something different in each one. So all sodium salts are soluble, sulfates are mostly soluble, sulfides are mostly insoluble. And there's a little Easter egg there. There's a link there that goes into, this is my favourite reaction. It's information about what's called the Maillard reaction. It's the reaction involving the browning and caramelization of meat.
Why is it your favorite?
Because I really love food, particularly a well-cooked steak. And I had steak last night and it was delicious. No, medium. Medium rare if I go out. Steps in predicting. Identify the possible products by switching the positive and negative ions. Write the formulas, write the equation and balance it, and then predict using the solubility table. Yeah? So identify possible products, write the formulas, write the equation, and then make a prediction using the table. So if I have silver nitrate and hydrochloric acid, switch the, pardon? There. That filtrate, don't worry about filtrate, that's fine. Filtrate is just the name given to what remains in solution. Yeah. We need to be able to predict whether a precipitation will occur or not. We jumped ahead by doing the prac first rather than the prediction.
So with this one.
Yep. Mostly.
So they're all the ones that are reactive.
Soluble. We're not talking about
Sorry,
reactivity. Soluble. Yeah.
Okay.
And
so
these
then,
are the exceptions.
if
So
I
if these are
was to
combined with sulfates or halides, they're insoluble.
Okay, so would I need to memorize all of this?
No, because you get given this on the exam.
Beautiful.
This is a mnemonic device, right, in case you find the table hard to read.
Right, thank you.
So here's an example. Silver nitrate and hydrochloric acid, when we mix them, swap the ions, step one, I get silver chloride and hydrogen nitrate. So there's my reactants, there's my possible products. We want to consider what the states are. It's going to be solid if it's a precipitate, aqueous if it remains in solution. No exceptions for nitrates for solubility. So we know that HNO3 will be aqueous. Chlorides binds with Ag to give us a precipitate out. And there we go. That finishes types of reactions.